The next topic in the appendix we wish to discuss are some supporting concepts in logic. And these are really more than anything some concepts that you're already familiar with, but it's some symbolic structure that we often use in mathematics and physics and the other sciences that kind of speeds up and abbreviates some of the processes that we're thinking about. In particular, what I would like to do is go over some of these symbols and special notations. For example, we have the symbol there exists. And often you don't want to write out there exists, so we just write there exists an X. And we can use the symbol of 3 dots for therefore. It just means therefore. There exists an X, therefore. We can use the symbol that looks like an E, but it's kind of a special symbol. There exists an X, therefore Y is a member of, and then we can use the other symbol, which is almost backwards from that, but slightly different. It means such that. We could write, there exists an X such that Y is a member of the set G. And it becomes a very succinct type of notation. This symbol is implies or leads to. This symbol is for all. We'd say for all X member of the set G, there exists a Y such that Z is greater than 4. Again, it's just notation. Isomorphic means one-to-one. It means if we compare 2 sets, for every item here, there's one item over here, and vice versa. Isomorphic means 1 here matches to 1 there. You're all familiar with the symbol for infinity, and we've already discussed several kinds of infinity. And you know what equality means and what not equal means. You may not be familiar with the fact that this, with 3 bars, either means equal by definition or it's identical. Like 4 is identical to 4, certainly. Also, you're familiar with the greater than, the less than, and also the greater than or equal to and less than or equal to. This symbol refers to includes. The set G includes X. We could likewise say X is a member of the set G. These brackets usually mean set. Okay, those are some special notations, and you can see how we've looked at that up here with there exists an X, which is a member of the real numbers, such that X is equal to X squared. And that implies that either X is equal to 0, or X is equal to 1, or X is equal to infinity. Now let's look at some of the logic or set theory elements. You're familiar with the elements 1 and 0, or equivalently true and false. The operations and, or, not, nor, NAND, equivalent, there are actually 16 logic operations. You know what I mean when I say Jack went to town. And Jill went to town. Means both of these occurred. Or I could say or, meaning Jack went to town or Jill went to town, which is very different. It means only one of these may be true. The other one may or may not be. This, nor, means either this is true or that is true. That would be an exclusive or you can have nor. I don't know what the symbol for exclusive or is. But a nor means neither this is true, nor is this true. In addition to the and, exclusive or, the nor, and or, we can have not. We can say, not Jack went to town and Jill went to town. That means it's true, both true that Jack did not go to town, that is false, and that this is true. Not inverses the truth on something. Then we can have NAND and equivalent. Altogether, there are 16 Boolean operations. And often they're symbolized with and being the symbol like this, means both, or is more of an exclusive, this or that. Not can be symbolized by this expression, which is a vertical bar and like that. And we also have for sets the union and the intersection. For example, we could look at the real numbers, the set of real numbers, and look at the union of that with the set of complex numbers. And that would give us the set of complex numbers, because the complex numbers already include the real numbers. So we can look at the concept of the union, or we could look at the intersection of the two sets. And the intersection of the two sets is all of the things that belong, whereas union is all the things that belong to either one of the sets. The union is what belongs to both of the sets. And of course, since the complexes consist of the reals and the imaginaries, the intersection of the two would be equal to the reals. That's something that's in both of the two. And here's the symbol for the set, and of course, most important, there's the null set, meaning the set with nothing in it at all. Well, this notation is very useful. It comes up all the time in mathematics and therefore in our expressions in science, logic, computer science, and so forth.